Hi everyone, welcome to the second installment of this field of view mini-series. So today we're going to be working on the actual field of view effect. So essentially what we want to do is just cast out a bunch of rays between our two view angles here and find all the sort of contact points of those rays and just construct a mesh out of that. So let's go into our field of view script and let's make a public float here called something like mesh resolution. So if we make a new method called, say, draw field of view, that mesh resolution variable is going to determine how many rays we cast out. So let's make an integer. We'll call this the step count, but we could also think of it as the ray count. And this we can just set equal to the view angle multiplied by the mesh resolution. So the mesh resolution is basically the number of rays we'll cast per degree. We're going to want to convert this to an integer, so let's just round it with mathf.round to int. Then we're also going to want to figure out how many degrees are in each step. So let's say float step angle size is equal to the view angle divided by the number of steps, so step count. We'll then want to loop through each of the steps, so let's say for int I equals 0, I less than or equal to the step count, I++, and we can say that our current angle that we're working with is equal to, first of all, our object's current rotation, so transform.eulerangles.y. We'll then want to sort of rotate back to the leftmost view angle, so we can just subtract view angle over 2. And then we'll just sort of rotate clockwise in increments of step angle size until we get to the rightmost view angle. So we can just add step angle size multiplied by I, which is our current step count. So if we wanted to just quickly preview what we've actually got here, we could say debug.drawLine from transform.position to transform.position plus the direction from the angle that we've just calculated, so pass an angle, and this is a global angle, so we'll say true, since we've already included the transform's own rotation in it, and we can multiply this direction by the view radius, and let's perhaps make the line nice red color. Alright, let's, we're going to have to actually call this method, so let's make a little update method, and from this we can call draw field of view. Okay, let's try that out. So just hit play. Currently the mesh resolution is 0, but if we bump that up, you can see that we're getting a bunch of rays being drawn between the two view angles. So that's great. Let's go back into the script though, and we're going to want to do a raycast for each of these angles in case there's an obstacle in the way. Having, of course, worked through all of this stuff in advance, I know that a little bit later on we're going to encounter some problems, and in order to resolve those we're going to have to do even more raycasting. So it kind of makes sense now just to make a method to handle the raycasting for us, so we don't have to keep writing it out each time. So this method will obviously need to return a bunch of information about the raycast. So let's first make a little public struct to store that information in. I'll call this the viewcast info. Alright, so this will need to know, first of all, whether or not the raycast hit something. We'll also want to know the endpoint of the ray, so just make a public vector 3 point, as well as the length of the ray, I'll just call that distance, and finally the angle that the ray was fired at. Alright, so let's just quickly set up a constructor, public viewcast info. So we want to pass in a value for each of these variables. So let's say bool underscore hit, vector 3 underscore point, float underscore distance, and finally float underscore angle. And then we just need to assign these real quick. So hit equals underscore hit, and well, you get the idea. Okay, so let's go ahead and create our viewcast method. So this will return a viewcast info struct. We can call the method viewcast. Just takes in a angle. Let's just specify that that's a global angle. All right. And then we can say vector3 direction is equal to direction from angle, pass in the global angle, say true. Okay. And then we'll want to make a raycast hit variable, just call that hit. And then we can say if physics.raycast from transform.position with a direction of direction, we can pass out our raycast hit variable, and we want the length of the ray to be the view radius, and we only want to collide with obstacles, so just pass in our obstacle mask. So if we hit something, we will return a new viewcast info. We just need to pass in the relevant information to the constructor. So this is if we did hit an obstacle, so we can say hit is true. The point will be hit.point. The distance will be hit.distance. And the angle will be the global angle that was provided to us. On the other hand, if we did not collide with an obstacle, we'll want to, once again, return a viewcast info. This time we'll say false, we did not hit anything. Instead of hit.point, we'll just say transform.position plus the direction multiplied by the view radius. And the distance will, of course, just be the actual view radius, since it goes all the way out, unimpeded. And we just pass in the global angle as well. Okay, so with that set up, let's go back to our draw field of view method, and I guess we can just delete this draw line, and let's create a new viewcast info. I can call this our new viewcast. This will be set equal to viewcast and pass in our angle. Okay, so we're going to want to maintain a list of all the points that our viewcast hits, so that we can actually construct that mesh. So let's have a list of vector 3s. We'll call this our viewpoints. Say that's equal to a new list of vector 3s. And so for each of these, we can say viewpoints.add new viewcast dot point. Okay, so in case you're unfamiliar with how we go about generating a mesh from a script, I'd like to give a quick rundown of how this will work. So say this is our character's position, and let's say we fired out 4 rays. So these are our 4 vector 3s in our viewpoints list. We now want to join these all up into triangles for our mesh. So let's call these vertices vertex 0, 1, 2, 3, and 4. So our first triangle, and we want to form each of these in a clockwise fashion. We'll go from 0 to 1 to 2, back to 0. Then the next one will go from 0 to 2 to 3, back to 0, and then 0 to 3 to 4, back to 0. So that's triangle A, B, and C. So apart from this array of vertices, Unity also wants an array of integers, where each set of 3 integers represents the index of the 3 vertices in the triangle. So in this example, our triangles array would be 0, 1, 2 for triangle A, then 0, 2, 3 for triangle B, and finally 0, 3, 4 for triangle C. So now let's say that the number of vertices we have, let's call that V, is equal to the number of viewpoints that we have, so these 4 over here, plus this 1 point that we need at the origin. So in this case we've got 5 vertices, we've got a triangle count of 3, so we can say that the number of triangles is equal to the number of vertices minus 2. So that means that the length of this triangles array over here is going to be the number of vertices minus 2 multiplied by 3, since there are 3 vertices in each triangle. Alright, so back in MonoDevelop, we can say that the number of vertices that we're going to have, so our vertex count, is equal to the number of viewpoints, so viewpoints.count, plus 1 for that sort of origin vertex that we need. So then we can say vector3 array, call this vertices, is equal to a new vector3 array with a size of vertex count. And then we want to create our integer array for the triangles. So this is equal to a new integer array with a size, as we discussed, of vertex count minus 2, all multiplied by 3. Now, one important thing to be aware of is that our view mesh is going to be a child of the character object, and that means that all of the positions of the vertices need to be in local space, so relative to the character. So if we want to set, for example, our first vertex, so vertices 0, equal to the transform's position, we don't say transform.position, we rather say vector3.0. Alright, so now we want to loop through the rest of the vertices and set them equal to the positions in our viewpoints list. So let's say for int I equals 0, I less than vertex count minus 1. The minus 1 is just because we've already set one of the vertices, so we can miss out doing one of them this time. And then we just say I++. Okay, so we want to say vertices I plus 1, so that we don't overwrite the first vertex we set, is equal to viewpoints I. Alright, now we also want to set that triangles array, so we can say triangles with an index of I times 3, so that will be the first vertex of each triangle. So each triangle starts at the origin vertex, so the next vertex in the triangle, that is I times 3 plus 1, should be equal to I plus 1. And then the last vertex in the triangle, I times 3 plus 2, should be equal to I plus 2. So in case that triangles thing is at all confusing, all we're doing is when I is 0, we're setting these 3 vertices. When I is 1, we're setting these 3, and when I is 2, we're setting these 3, and so on for however many vertices we have. Now, of course, we don't want this to go out of bounds of our array, so let's just say that we only do this while I is less than vertex count minus 2. Alright, so let's go up to the top of the script, and we just want to create a public mesh filter variable. We can call this our view mesh filter. And then we also want a private mesh variable called our view mesh. And then in the start method, we'll say view mesh is equal to a new mesh. And we can maybe just set its name, so viewmesh.name is equal to just view mesh, I guess. And then we want to assign that to the view mesh filter, so say view mesh filter.mesh is equal to that view mesh we've just created. Alright, so now if we go into Unity, just select our character, let's say create empty child, and we can call this our view visualization. Alright, we want this to have a mesh filter component as well as a mesh renderer component. We can maybe just set cast and receive shadows both to off. And let's go into our character and just assign that mesh filter to our mesh filter variable. Might as well just set mesh resolution up to 1 now. Alright, so now we can go down to the draw field of view. Right at the bottom here we can say viewMesh.clear, so we reset everything in the view mesh to start with, and then we'll say viewMesh.vertices is equal to our vertices array we've created. viewMesh.triangles is equal to the triangles array we've created. And then finally we can just say viewMesh.recalculate normals. Alright, so if we run this, we should see something happening. Okay, so things are pretty wacky here at the moment. I suspect the problem is that, remember when I was saying how everything must be relative to the player's position? Well, these these viewpoints that we're setting the vertices to are global points, so we want to convert those to local space points. So we can just say transform dot inverse transform point and pass in the viewpoint. So now if we save that, let's go back and run this again. So this is looking much closer to what we want. One thing that's very important though is that our draw field of view method be called only after the controller has finished rotating, otherwise we get this very sort of jittery look. So let's go back and just change this update method to a late update method, so it only gets called after the controller has updated. And this should already look much smoother. So one problem we're having at the moment is with the edges of obstacles. You can see as we rotate, there's still this sort of jitter that's happening there. So one way we could fix this is just by increasing the mesh resolution. So I set that to 10. The jitter should now be basically entirely gone, and that's very nice. But that does mean that we're casting about 870 rays per frame, which is a tiny bit excessive. So basically what we're going to be doing for the rest of this episode is finding a slightly smarter way to solve that edge problem. While we're here though, let's just quickly hop into the materials folder. I'm going to duplicate this and call this the view visualization material. Okay, so we can set that to, say, fade, and maybe just make this a sort of transparent white color. And then we can just apply that to the material slot of our mesh renderer. So now instead of that ghastly pink, we get a nice transparent white. So here's a sort of close-up of the edge jitter problem. And as you can see, what we really need is to always have a vertex at, or at least very close to, the edge of the obstacle. Okay, so here's a diagram with a character and an obstacle. Let's say we're firing out our rays and the first one hits the obstacle. We fire out a second, that one also hits the obstacle, and then we fire out a third, and that one misses the obstacle. So now we know that the edge is somewhere in between those last two rays. So we label those the minimum and the maximum, and we fire out a new ray halfway in between the two. Let's say that one also misses the obstacle. Now we can say that is our new maximum, and the edge is located somewhere between min and max. So once again, we fire a ray right in between the two, and this time let's say it hits the obstacle, so that now becomes the new minimum, and once again we fire a ray out halfway between the min and the max, and as you can see we very quickly sort of narrow down the space and find the edge. Okay, so we're going to have a find edge method, so once again I want a little struct for the information that it's going to return, so call this time edge info, and this just has two public vector 3s, a point A and a point B. So one of those will be the closest point to the edge on the obstacle, and the other the closest point to the edge off the obstacle. So we can just quickly make a constructor, public edge info, takes in vector 3 underscore point A, vector 3 underscore point B, and it assigns those point A equals underscore point A, and point B equals underscore point B. Okay, so when we're doing this loop to find all of the viewpoints, we're going to want to know whether or not the previous viewcast hit an obstacle or not. So let's, outside of the loop, create a viewcast info, and we call this old viewcast. Set that equal to a new viewcast info. Alright, and at the end of the loop, we'll always just set the old viewcast equal to the new viewcast. Of course, on the first iteration, when I is equal to 0, the old viewcast won't have been set yet, so we can't really do anything. So let's just say if I is greater than 0, then we want to check if either the old viewcast hit an obstacle and the new one didn't, or the old one didn't and the new one did, because then we need to find the edge. So we can say if old viewcast.hit is not equal to new viewcast.hit. Then we're going to want to find the edge. So let's make that method. It returns a edge info variable. We'll call the method findEdge, and it takes in two viewcasts, a min viewcast and a max viewcast. Alright, so at the beginning we can say float min angle is equal to min viewcast.angle, and float max angle is equal to max viewcast.angle. We'll also want to make a vector3 min point. By default that can be equal to vector3.0, and likewise vector3 max point should be equal to vector3.0. So we're now going to want to have a loop where, as I described, in each step of the loop we will cast out a ray in between the min and the max angle. So the more times we run this loop, the more accurate our edge detection is going to be. So let's actually create a variable up at the top here. We can call this a public int. Let's call this the edge resolve iterations. Alright, so we'll run this for int I equals 0, I less than edge resolve iterations, I plus plus. So we'll want to find our new angle, so just call that angle. It's equal to the minimum angle plus the maximum angle, all divided by 2. We'll then cast out a new viewcast. Let's say viewcast info new viewcast equals viewcast, and we'll give that the angle. We can then say that if the result of the new viewcast hit is the same as the min viewcast hit, then we're going to want to set the min angle equal to the current angle and the min point equal to the new viewcast dot point. Otherwise, we'll want to do the same thing with max angle, set that equal to angle, and max point get set equal to new viewcast dot point. Okay, then at the end, we'll just want to return a new edge info, and we'll pass in the min point and the max point. Okay, so up here, we'll say edge info edge is equal to find edge. We'll give it our old viewcast as the minimum and the new viewcast as the maximum. Then we'll want to add both of those edge points to the viewpoints list, provided that they've been set. So in other words, they don't still have their default value of vector3.0. So we can say if edge.point A is not equal to vector3.0, then we'll say viewpoints.add edge.point A, and we can just copy this to do the same thing for point B. So if that's not equal to 0, then we add point B. So here's that same example from before, only this time we've got the findEdge method implemented, and it's running with a edge resolve iteration of 6. And as you can see, it's handling those edge cases far better than it was previously. There is still a problem, however, and that is if you consider this scenario where our view mesh is being cast against two different obstacles, it doesn't realize that it needs to search for an edge because the first ray hits something and the second ray also hits something, only it's an entirely different obstacle. So what we'll want to do is implement some sort of distance threshold, so even if the two consecutive rays both hit something, if their hits are a certain distance apart, we'll consider them two different objects and we'll run our findEdge method anyway. So let's go up to the top of the script and make a public float. You can call this edge distance threshold. Alright, and then over here, where we're trying to decide whether or not we should do our edge detection, we can make a bool called edge distance threshold exceeded, and this will be equal to, we first get the distance between the two hits, so the absolute value of old viewcast.distance minus new viewcast.distance, and we want to see if that is greater than the edge distance threshold, and if it is, then our edge distance threshold exceeded bool will be true. So we can say we do our edge detection if the old viewcast hit is not equal to the new viewcast hit, or if both the old viewcast hit something and the new viewcast hit something, and we've exceeded the edge distance threshold. Okay, we'll want to make a similar modification in our find edge method. So let's just copy this edge distance threshold exceeded bool, and we can paste it in over here. So we'll just change old viewcast to the min viewcast, and then we'll say we set the min angle and min point if the new viewcast hit is equal to the min viewcast hit, and we have not exceeded the edge distance threshold. Alright, so now if we go into Unity, let's just set our edge resolve iteration to something like 4, and I'll set the edge threshold distance to maybe 0.5. So now if we try this out, you can see that our edge is nice and smooth over there, on this side as well, and even with 2 obstacles, it still works very nicely. Alright, so that concludes episode 2, and possibly the series. There have been a couple of requests for some additional features, which I'm currently experimenting with, and so I may or may not decide to release a 3rd episode with some of those. But regardless, thanks for watching. I hope you've enjoyed the mini-series and learned something useful from it. So until next time, cheers.